This is the first example that we are going to discuss under simple harmonic motion. Let's start with the problem. A particle of mass m is connected to a string. This is an elastic string of natural length L and modulus of elasticity is lambda. The other end of the string is connected to a point O on the ceiling. The particle is released from O. So let's say this is the ceiling, point is O. This is the natural length. Natural length is L. Then because of this connected mass m, there will be a weight mg resulting in an extension. Extension is not given. Let's mark it as x. The modulus of elasticity is lambda. Now they are saying the particle is released from O. Now the problem is moving to a different direction. Now the particle is here. It will continue its path along this vertical line. Let's say this is our natural length L. Then there will be a certain velocity for this mass m when it passes this natural length. After this location, the string is going to extend, but it is going to extend not only because of this weight, because of the velocity as well, because it is having a certain velocity. Then first let us use kinematic equations to find v. For that we can apply, let's say this natural length location as A. O to A, I am going to apply v squared equals u squared plus 2as. Then final velocity at A is v. Initial velocity is 0. There was no velocity. We are just releasing the particle. Then acceleration downward is gravitational acceleration. Displacement between O and A is L. Then what is v? It is square root 2g L. Now we have to start from our characteristic equation. What is the characteristic equation? X double dot equals minus omega square into x. First we have to derive the characteristic equation for any simple harmonic motion. So let's consider a general point. We are considering a general point along this path with a separation x. We are taking x. Then we can apply F equals ma to this motion downwards. Downward forces, what are they? We have mg and resistive force is T. Then the forces are mg minus T equals mx double dot. If the separation is x, our acceleration is second derivative of x, x double dot. Then what is the tension? We discussed the tension equation in our first video, that is modulus of elasticity given in the problem, lambda into extension. Now what is the extension? It is x over natural length. Natural length is L equal mx double dot. Now I have to subject x double dot and take that constant, angular velocity constant, omega square out from these two. Here we have m. I will write that here in this step. And here mg minus lambda x over L. You know our characteristic equation is in this form. A constant to be determined into x. Sometimes this can be given, not sometimes actually, in most of the cases you have this kind of an expression here, x minus a constant. So as the first step we must have x. So when I am going to take the common factor out from these two, I have to consider this term with x as my first step. Then only I can have x in this location. Then minus lambda over L have to be taken out. Inside the bracket I am having x. Then here, since this is plus, I have to put minus. We have mg here, but we didn't have lambda in numerator, so I have to divide that. And we didn't have L in denominator, I have to multiply. Then I am going to divide this equation by m. Then I am having lambda over ml times x minus mgl over lambda. So this is the characteristic equation of this particular particle performing simple harmonic motion. So we have to write a statement for that. This is in the form of characteristic equation of simple harmonic motion, where we have to mention that constant omega square is equivalent to lambda over ml. Here we have minus omega square, therefore minus can be neglected. And center of motion. How to find the center of motion? We have to equate this bracket into 0. Equate this bracket into 0. Then subject x. That is the center of the simple harmonic motion. Center x is equivalent to mgl over lambda. So we have to find omega square constant and center x. Calculation of center x is this. We have to equate this bracket into 0 and subject x. Now after showing this movement in this form, simple harmonic motion, we can find its amplitude. How to find the amplitude? We have to apply our second equation. Velocity square equal omega square into amplitude square minus displacement or extension square. For that we have to consider a point along this simple harmonic motion where we know velocity, because I am going to find amplitude. To find amplitude we must know these three. We have already calculated omega square, x is the separation, then the velocity. This is the point where we know velocity. This is that velocity. Then what is the separation to this point A from our center? So this is the separation of the particle from center. So center is mgl over lambda below A, because x is measured from A. This arrow indicates x. Therefore, center of this simple harmonic motion is this much below A. Then let's say that center is somewhere here. Then what is the separation to this location where we are going to consider the velocity from center? It is mgl over lambda. If you didn't get, I repeat, in this equation x is the separation of the particle from center. So we are going to take the velocity at A, then separation of the particle from center is this length. Then from this calculation we have found x from here to here as mgl over lambda. Then this separation is mgl over lambda. Then velocity is 2gl square root its square. Omega square is lambda over ml into amplitude square minus separation is mgl. We have to square that over lambda square. Now cross multiply, you have 2 mg L square over lambda equal amplitude square, this one. Then our amplitude is 2 mg L square over lambda plus m square g square L square over lambda square square root. This is the amplitude of the motion. Now we have to mark this obtained amplitude in our diagram. Let's consider this new diagram which I have enlarged. So this is this amplitude calculated, that is A. The particle travelled under gravity from O to A and there was a certain velocity v. After that it is performing a simple harmonic motion. This is the center, this is the amplitude. Now this particle will move back a similar distance upward, that is above C. We don't know whether it is more than this or less than A. Then in the problem they are asking to find the time taken by the particle to reach O again is given by this expression. Particle was released from O. From O to A there is a particular time which the particle moved under gravity. Then from A it is performing a simple harmonic motion. Again from this amplitude location to A it is continuing another simple harmonic motion upwards. So as my first introduction video, if we want to find a time, we have to complete an arc starting from this amplitude location upwards. So this is that arc. We don't know the finishing point. Then the second construction is constructing a line to connect this arc from finishing point of the motion. This is the starting point, this is the finishing point, and this is the area or that arc the particle is going to perform simple harmonic motion. This is the center. Then center to this is the amplitude, and similar to that here also we have an amplitude, center to circumference. These two are like two radii of this arc or the sector. This is the x what we calculated here. We calculated the center of simple harmonic motion x as mgl over lambda, that is equivalent to this mgl over lambda. Now look at the relationship they have given. There we have tan inverse this expression. From this we can get a hint. The angle we have to find is tan ratio, that is obtained from the expression given. So the angle we have to find, let's say it is theta, it is a tan angle. Tan angle must be 2 lambda over mg square root. This hint can be taken from the expression. Keeping that in mind, we have to mark theta in this diagram. So this amplitude A is equivalent to this length. This length is also known. Here we have phi minus this angle, 180 minus angle. If I mark my theta here, the completed angle directly becomes theta. But here the angle, given angle is 180 minus theta. So this is that covered angle. If this covered angle is to be phi minus theta, I should mark my theta here. So that is a logical thinking. Here the angle is 180 minus a small acute angle given from tan. In order to get this covered angle 5 minus tan inverse this, I have to mark theta here. Then only I can write this as total 180 minus this small theta angle. Then what is tan theta? It is opposite divided by adjacent. Then how to find this opposite side, length of the opposite side? There also we have to do a small logical calculation. This is amplitude. This is a big expression with a square root. We can't use that. This A is what we have here, from here to here. This is this amplitude. Then mgl square over lambda square, mgl over lambda is what we have here. Then think this obeys Pythagoras relation. Hypotenuse square minus this length mgl over lambda square will be equivalent to the square of this. Consider this as a right angle triangle. This length is equivalent to a square amplitude square minus this length square. Okay, then from this relationship I can say this one is equivalent to what we have here. What is that? 2mg L square over lambda, but it is a length. I have to take the square root. This is equivalent to square root of what we have here. Now tan theta is equivalent to 2mg L square over lambda square root divided by opposite side, adjacent side, mgl over lambda. Then we can simplify these two and cancel mgl terms and get 2 L over, here these L's get cancelled because L square square root is L, L get cancelled with this L. Here we have only 2 lambda over mg square root. Square root mg get cancelled with one of the square root mg's in denominator, then square root mg is remaining. Then this lambda, this square root lambda get cancelled with this lambda, then one square root lambda is remaining, that is going to the numerator. Square root 2 is there. Then theta is equivalent to tan inverse 2 lambda over mg square root. So what we have here. Then time taken by the particle to travel from this location, let me label that as D. D to A or A to D, both times are equal. Let's mark it as AD. Time taken for this movement is given by the total angle covered. What is the total angle? 5 minus the small theta divided by omega. That is 5 minus theta. Theta is tan inverse 2 lambda over mg square root divided by omega. I'm not going to substitute omega still. Then we have to find the time taken by the particle to move under gravity from O to A. O to A. For that we have to use S equals ut plus half at squared vertically downwards from O to A. Displacement is L. From here to here it is L. Initial velocity is 0. We are just releasing the particle. Then it is g over 2 t square. Then we have the t as 2L over G square root. Then we can find the total time. Total time taken by the particle to reach O again, O to A to D, and again D to A and A to O. Total time is equivalent to time AD plus time OA into 2. We have to multiply everything by 2. O to A is twice, A to D is also twice. Then 2 times A to D time is 5 minus tan inverse this thing over omega. Here we have 2L over G square root. Then how to simplify this omega? From this calculation we have omega as square root lambda over ml. Omega is square root lambda over ml from this answer. Since our omega is in denominator, we have to take the reciprocal when I am going to write omega in numerator. Then this becomes ml over lambda square root. Because omega is in denominator, if I am going to write that in numerator, I have to take the reciprocal of this fraction. Here we have 2L over G. Is that the answer we have? 2L over G? Yes. Yes. This is the expression that we want to show.